Picture this, the very beginning of the universe, a hot sea of particles and radiation. In that cosmic soup, protons and neutrons fused to create the first atomic elements. Over the next several 100,000 years, atoms formed, beginning to clump together under gravity's pull. These large clumps collapsed and birthed the universe's first stars. These stars, made of pristine material from the Big Bang, were behemoths, roughly 25 times the typical mass of current stars. Their size brought about a short lifespan, but their death paved the way for the universe to morph into what we know today. Created from large clumps of matter, these early stars were giants, with an average mass of 10 times that of our Sun. Their lifespan was brief by cosmic standards, but in their short lives, they emitted a radiance thousands to millions of times that of our Sun. As they consumed their hydrogen fuel, they began to contract, and in their death throes, they unleashed a chain of elemental creation that, well, let's just say it resulted in a phenomenon that still fascinates us today. But hold on to your hats, because you'll hear all about that soon enough. What's up, my amazing and curious folks? Ready to unravel the mysteries of the universe together? I'm your host, Cesar, and with me is the vibrant and ever-inquisitive Sonia.
Hey everyone, so excited to dive into today's topic.
Fantastic. Now, if you're as curious as we are, don't forget to subscribe to our channel and hit that bell icon so you don't miss out on any of our daily episodes. This is the Curiosity Wonderland. Let's take a journey into the unknown, shall we? Now, imagine the very first stars in our universe. They were born from the pristine material of the Big Bang in a universe devoid of heavy elements. These stars were enormous, 25 times the typical mass of stars formed in our time. And because of their size, they burned through their fuel rapidly, going through their life cycles at an accelerated pace.
Could you give us an example to put this into perspective?
Imagine a candle. A small candle will burn slowly, glow softly, and last a long time. But if you had a giant candle with 25 times more wax and a much larger wick, it would burn much brighter and much faster. It's similar with stars. The larger they are, the faster they burn through their fuel, and the quicker they reach the end of their life cycle.
But you said these first stars were essential for the universe we know today. How so?
Right. The death of these first stars actually gave birth to something new. When they stopped burning, they would collapse and cause a supernova, an enormous explosion that spread the elements forged inside the star throughout the universe. It's a cycle of creation and destruction that led to the universe we know today. But the most fascinating part is yet to come. Let's continue this cosmic journey. Now, these first stars were unlike anything we see today. They were enormous, with an average of 10 solar masses, and many even reaching hundreds of solar masses. And some, believe it or not, likely surpassed 1,000 solar masses, which is something we don't see in modern times.
Can you put that into perspective? 1,000 solar masses is quite hard to wrap one's head around.
Think of it like this. Our sun is massive, right? Now imagine 1,000 suns crammed into a single star. That's the extreme size we are talking about. They are so massive and bright that they outshine millions of suns.
And these massive stars lived a very short life, didn't they?
Yes, indeed. The larger a star, the faster it burns through its fuel and the quicker it dies. To give you a comparison, a star like our sun might live around 10 to 12 billion years before reaching the end of the fuel in its core. But these early stars, with hundreds or even thousands of times the mass of our sun, are expected to have a lifetime of just 1 to 2 million years. That's less than 1/100% of our sun's lifespan.
That's incredible. So what happens when these giant stars exhaust their fuel?
Well, when these stars burn through their hydrogen, their cores contract and heat up, fusing helium into carbon. This process continues with the star fusing heavier and heavier elements, from carbon into neon and oxygen, then to magnesium, silicon, and sulfur, and eventually reaching iron, nickel, and cobalt. When they can no longer fuse any more elements, they end their lives in a spectacular supernova explosion, spreading the fruit of their nuclear fusion throughout the universe. It's a truly dramatic ending. Now let's talk about what happens after a supernova. A supernova is the typical fate for a star greater than about 10 solar masses. The cycle of nuclear fusion in these massive stars creates a large amount of heavy elements, building elements up to around iron. Then a supernova occurs.
So the star explodes, and then what?
Great question. The elements then experience a rapid bombardment by neutrons as they get blasted off back into the interstellar medium at the moment of the supernova's detonation. They typically rise up the periodic table to reach zirconium, with heavier elements capable of being formed out of those now enriched, heavier than ever before elements. What the supernova leaves behind, which is the former core of the progenitor star, is typically a neutron star. A collapsed mass that's greater than our sun, but no bigger than perhaps a dozen miles from end to end.
That's truly fascinating. Is that the end of the story?
Not quite. In these dense, early environments, neutron star collisions should be relatively common, giving rise to what we call kilonova events. These are catastrophic events where two neutron stars collide and either form a larger neutron star or a black hole. This collision converts mass into two types of radiation: electromagnetic and gravitational. About 5% of the total mass gets expelled in the form of heavy elements. So, the death of these stars is not an end, but a beginning for other celestial bodies. It's quite the cosmic saga, isn't it? These neutron star collisions, they don't just stop at creating a black hole or a larger neutron star. They actually result in explosive reactions. These reactions emit gravitational waves, neutrinos, and electromagnetic radiation of all types. They also expel large quantities of heavy nuclei.
I see. So these reactions create more heavy elements?
Exactly. These heavy nuclei climb all the way up the periodic table, producing the majority of the heaviest elements in the universe. Together, supernovae, neutron star mergers give rise to the full suite of elements that make up the periodic table.
That's staggering. So all the elements we know, they are all a result of these cosmic events?
Yes, indeed. Even the heaviest elements that we know of are a result of these cataclysmic events.
Going back to the mass of these first stars, they were significantly heavier than our sun, right?
That's right. These first stars were incredibly massive. The so-called average star might be around 10 times the sun's mass, but many were far above average, reaching hundreds or even 1,000 times the mass of our sun.
And these larger stars, they burned through their fuel even faster, didn't they?
Absolutely. The larger the star, the faster it burns through its fuel. Shining as bright as millions or even tens of millions of suns, each one has a unique fate, largely depending on its mass. For those that are supermassive, their collapse results in a black hole. When a neutron star crosses a certain threshold, it collapses all the way into a black hole, which is the second most common fate for the first stars. But something truly exciting happens with stars of even higher masses. The temperatures inside the star reach such great levels that a special process begins to take place.
What process is this?
Well, there's enough free energy within the star's core that the photons flying around can spontaneously form particle-antiparticle pairs. Two photons can transform into an electron and positron if energies are high enough.
And what does this mean for the star?
This transformation carries with it some new physics. The radiation pressure from the photons was what held the star up against gravitational collapse. But the loss of photons means a loss of pressure, and the star begins to collapse further. As it does, the temperature goes up, making it more likely that photons will convert into electron-positron pairs. This becomes a runaway process, and the star's core collapses entirely.
Wow, that's incredible. What happens next?
This process leads to what is known as a pair instability supernova, or if you prefer colorful language, a hypernova explosion. These are extremely rare in the modern universe, but the first stars should have had many instances of this type of cataclysm. Depending on the mass, this could lead to a black hole at the core while blowing off their outer layers, or destroy the star entirely, giving rise to a much more severely enriched portion of the interstellar medium.
So the universe's first stars were truly spectacular in their life and death.
They really were. Their fates varied greatly, and each one played a significant role in the cosmic drama that has shaped our universe. It's theorized that stars of different masses reach the pair instability threshold at different times in their life cycles. This makes the elements they expel, and ultimately the way they enrich the universe, a variable that we don't fully understand. But we do have a good theory of how a star will evolve, live, and die based on two factors: its initial mass and the fraction of heavy elements it's born with.
Wait, so you're saying the destiny of a star is predetermined at birth? Sort of like a cosmic DNA?
That's a great way to put it. Yes, the initial mass and the metallicity of a star set the course for its life. But interestingly, the biggest uncertainties in this calculation are at the extreme low metallicity end, meaning the stars made out of the most pristine material.
What do you mean by pristine material?
By pristine, I mean material that's passed through multiple generations of stars in the past before forming the stars that are now present today. And it's very difficult to find a star with less than about 0.1% of the heavy elements found in our sun.
So even though we understand a lot about the life and death of stars, there are still mysteries out there?
Absolutely. For instance, stars of severely extreme masses or that undergo just the right set of processes could experience a fate that doesn't result in a cataclysmic explosion at all. Instead, these massive stars could directly collapse into a black hole without a supernova of any type.
So the universe is full of surprises. It seems like there's never a dull moment in the life of a star.
Once an event horizon forms, collapse down to a black hole is almost inevitable.
Wait, event horizon?
Yes, an event horizon is a boundary in space-time beyond which events cannot affect an outside observer. In layman's terms, it's the point of no return around a black hole.
So stars can just disappear into a black hole?
Indeed, we've observed stars that were once visible simply vanish. There's no radiation in any wavelength of light, no remnants. They've seemingly directly collapsed into a black hole.
That's mind-blowing.
And these black holes are the seeds that spawn the supermassive black holes at the centers of galaxies today.
So not only do black holes come from stars, but also from matter that never passed through a stellar phase.
Correct. Both stars and gas clouds contribute to the formation of these massive black holes.
So in essence, the universe we know today began to shape after the deaths of these massive stars.
Exactly. After millions of years of cosmic evolution and the death of these stars, the universe began to resemble the one we inhabit today, with its heavy elements and black holes. It's like a cosmic circle of life. So let's take a moment to appreciate the grand scale of this cosmic process. We've followed the journey of stars from their birth, seen how they evolve and die, and understood their legacy in the cosmos, the elements they release, the black holes they may become. It's a truly remarkable cycle of cosmic phenomena.
Indeed, it's like a cosmic dance full of mystery, splendor, and beauty.
We may not yet understand all the variables, and the universe still holds many secrets. But what we do know is that every star, every speck of dust, and every black hole contributes to the grand tapestry of the cosmos. The universe we know today was shaped by these processes, and they continue to shape it. It truly is a cosmic circle of life.
And we're all part of it, which is both humbling and wonderful.
So we've journeyed from the early cosmos, where particles and antiparticles clashed and annihilated, leading to the formation of the very first atoms, the first building blocks of matter. The universe then cooled down, and neutral atoms formed, marking the turning point for matter to start clumping together due to gravitational pull. This gave birth to the very first stars, massive, brilliant, and short-lived, whose spectacular deaths spread heavy elements throughout the cosmos and created the seeds for the supermassive black holes we see today.
It's a cosmic narrative of creation and destruction, gestation and birth, life and death. It's the story of us, of our universe, and everything in it. It's a tale of how everything we know, everything we are, and everything we see has come to be.
And to think we are all stardust, dancing in the light of long-dead stars.
Absolutely fascinating. Thanks to all of you for joining us on this cosmic journey. If you enjoyed this episode, please show your support by blasting that like button, leaving a comment, and sharing the episode with your friends.
And always remember, the universe is full of mysteries waiting to be uncovered. So keep looking up and keep wondering.
Until next time, goodbye and keep exploring the universe.
I found this incredible cosmic story on the Big Think website. The article, titled, "What Was It Like When the Very First Stars Died?" was penned by Ethan Siegel and published on December 22nd, 2023. The full URL is in the video description if you want to delve deeper into the subject. All right? Now I'm off.